In this video, we'll begin our discussion of Green's theorem. I'm not going to prove this theorem. Some of our book will talk about like kind of where it comes from in a very loose terms. Give that a look. Also, there are plenty of very rigorous videos about where this formula comes from. At this point, with working with this integral so much, right? This looks like the same thing we've been doing. And notice there's a new symbol there. This new symbol has to do with the region that we're talking about. So the region we're talking about has to be a simple and a closed. Okay, simple, if we remember this was in the last section, but the simple sections, simple curves, right, don't overlap itself. Not simple would overlap itself in some sense, and it can even be, barely, something like that. If it overlaps itself, it is not simple. A closed is that it closes itself, right? It's not going to be something like this. So it has to be simple, has to be closed. And then another thing, and this isn't going to pop out as a problem at all, we'll just have to make sure we note it, is that it's oriented counterclockwise. That means it's closed, so it has to be some kind of circular region, right? That ends, not even circular, sorry, stops and ends. It's not just a line. It has to be moving, the path has to be moving counterclockwise. We're just going to make sure in our pictures that we do that. And then encloses, and then we have these definitions over here, connected and simply connected. So remember, connected means I can pick any 2 points in my region. If my region's like this, if I pick 2 points, I can pick a path that is in the region to get from one point to the other point. A non-connected region would be 2 open regions like this. Call that the same region. If I put one here and one there, there's not a path from one to the other. Simply connected, that means that with some region, let's take this region here. If I put a space in between here, an open space, I can contract it down to a single point that is inside that space. So simply connected means that. Not simply connected would mean like I have a region and then there's a hole in the region and I try to put this like boundary around it. I can't contract it down to a single point that is in my space. So we just need to make sure those two things hold, and we can use this theorem. This theorem is very nice. We have that form. We also can take it from this form. This means that circle right there means that my region is simple and closed. Right? It's just a new symbol that means that it is a path C, but is also simple and closed. All right. What this formula does is going to switch it to a double formula over a region R. Right, so this is just like earlier in our class with respect to its area. And what's great is that these two things are going to usually be decently simple, and it's going to make my integral very, very nice. And let's take a look at it. Also, notice there was nothing said about conservativeness. It does not have to be conservative or not conservative. We'll see what happens when it is a conservative vector field. Some of you guys may be able to look at that definition and be like, oh yeah, that would happen. We'll get there. All right, let's do an example. A lot of these I'm not going to integrate at the very end because I would like to keep these videos decently short. So we have this integral, a line integral, over a closed and simple boundary, or closed and simple curve C for that vector field that's here. Now, our vector field, if you're unsure, if I have a vector field and I have two parts, M and N, these are M and N. Those are my vector fields. That is how that is set up. Path C is done in the integral, and then M and N, that's my vector field. All right, we have C is the boundary of the region bounded by the curves. We have this is a parabola, that's a vertical line, and then we have the x-axis. I went ahead and drew my picture because I can get a bit obsessive when I'm doing my pathways like this or these regions. So I just did it before so you didn't have to watch me obsess. So my path is this closed, and you can see it's not perfect here. There we go. See, I can tell you I kind of obsess over it. So let me go back and just not do it perfect. So we have that, there, and then we can say that we go that way, counterclockwise. The path is simple. It doesn't overlap itself. It is closed because it is a closed boundary. And then the region inside is simply connected. I can contract any area. And it is also connected. Take 2 points in R, I can connect them. So we're talking about that pathway. The reason the region is important is because we're about to switch this to a double integral of R. All right, so let's do that. we know, first, let's figure out these two things. If you notice, those are the things that we determine. If those two things are equal, then it was a conservative vector field in 2 space. So we're just doing that. If these two things are equal, then it's conservative. And we'll talk about that once we get there. Okay, so n with respect to x, okay, that's 1. And then m with respect to y, okay, that's going to be, we just get the exact same thing. That means n minus x, the partial of n with respect to x minus the partial of m with respect to y is just 1 minus x e to the y. So I know that this line integral, so I like to rewrite it here. This new symbol is also fun to draw. It feels fancy, I guess. There we go. This, I'm just rewriting my problem. This is equal to my region over R of 1 minus x e to the y times dA. Well, I can now switch this to my double integral with x's and y's. I look at my region. I can see that x runs from 0 to 2. And then y, the reason I chose y first is because it has my functions. Okay, I got y equals 0 up to that parabola. And then I just throw this in here, 1 minus x e to the y. And then I just keep my bounds where they make sense. And now we have a double integral that we can do. I'm not going to spend video time doing a double integral because the hard part here is that setup. This answer, if you would like to check yourself, is 1 over 6. My 6 got kind of weird there. 1 over 6, 31 minus 3 e to the 4th is the exact answer if you would like to check your answer. So that's it. That's Green's theorem. Nice. It makes it very nice. I think this method is the most preferred for me. But again, this method is only used when this is a closed, simple boundary, boundary, and then the region itself is connected and simply connected. As long as we have that, we can use Green's theorem. It doesn't even require conservativeness.